In general, the force on the string is called the tension force. So let's do a problem based on that. In this problem, two masses m1 400 gram and m2 1.5 kilogram, they are hanging from a pulley. We are assuming that pulley and string, they have very small mass, okay, and there is no friction. Our goal is to find what is the acceleration and force on the string, okay. So first step is we have to find the three-body diagram for both block. So from this picture, we see that M1 mass is smaller and M2 mass is bigger. So we can guess that this mass will go up and this mass, M2 mass, will go down. So let's draw the three-body diagram for these two masses, okay? So there is three-body diagram, three-body diagram for M1. So the mass M1 is represented by dot. So force on the string is T1 and force due to the earth is W1, which equals M1 times G. So here T1 is the tension force in the string for mass M1. Similarly, we can draw the free body diagram, for mass M2. So mass M2 will be represented by dot. Force on the string is T2 and weight W2 equals M2G. So here T2 is the tension force in the string for mass M2. This string passes through the same pulley and frictionless. We can assume that this T1 and T2 has magnitude same. So T1 magnitude, T2 magnitude is same. So we can write just T1 and T2 are same. So just say T instead of T1 and T2. Okay. This mass M1 is moving up with acceleration A1. The mass M2 is moving down with acceleration A2. Since M1 and M2 are attached with the same string and through the same pulley, frictionless pulley, so we can fairly assume that magnitude of acceleration A1 and magnitude of acceleration A2 is same. So A1 magnitude and A2 magnitude same. So we just say A. So be careful that vector A1 and vector A2 are different. Here magnitude are only same. So based on this force diagram, we can solve the problem using the Newton's second law. So let's start with Newton's second law. So Newton's second law, A equals F net force over mass. Let's use this equation for mass m1. So a1, we just write a for the mass m1. So acceleration equals net force. So we have two forces here, T1 vertically up and weight vertically down. So I can just write T plus minus m1g over m1. I just took the coordinate system of positive and down and negative. Okay. So plug the number over here. So acceleration A equals T minus mass is 0.4 kilograms, value of G is 9.8 over 0.4. For simplicity, to solve this problem, I just multiply both sides by 0.4. That's how I got it. 0.4 times A equals T minus T minus um, 0.4 times 9.8, which will be 3.92. So we have two variables. So I call it equation 1. We have A unknown, T unknown, so it remains as equation. Let's do the similar step for mass M2. For mass M2. So again, A equals T minus T plus minus M2G. This minus comes because of the coordinate system over M2. But one thing important we need to consider here is this. This should be minus, but at this time, mass M2 is falling down. Okay, so A1 and A2 has same magnitude, but A1 is vertically up, A2 is vertically down. Okay, so now again, as before, we can plug the numbers. We don't know acceleration, so A remains as it is. So T minus M2 will be replaced by 1.5, G will be replaced by 9.8 over 1.5. So to solve this, I multiply both sides by 1.5. That gives me negative 1.5, negative 1.5A equals T minus 14.7. So this is the second equation. So we need to solve these equations to find A and T. So solve equations 1 and 2 to get acceleration and force on the string. Okay, that. This can be done in many ways. I just go through one of the way. Because this is algebra, we can do by various ways. So just I try one approach. So isolate T from equation 1. Okay, equation 1. So equation 1 is 0.4. So equation 1 can be written as T equals 0.4 times A plus 3.92. So I have to plug T in equation 2. In equation 2, negative 1.5A, the T could be replaced by this. So in place of T, I can write 0.4A plus 3.92 and negative 14.7. Rest is algebra. So maybe I can do negative 0.4 a to both sides. Then this will cancel out. So I'm left with negative 1.9a equals negative 10.78. Then I can divide both sides by negative 1.9, negative 1.9. That gives me a equals 5.67. Let's see the number. 5.67 meter per second square. That's how we get the acceleration. Now, you can plug the value of a in either equation 1. You can plug this number over here or in equation 2. So I just choose 1. So from equation 1, 6.4 times, oh no, may not be 6.4. Let's see the equation 1. No, it is 0.4. So it is 0.4 times 5.67. So 0.4, 5.67 equals t minus 3.92. That gives me 2.27 equals t minus 3.92. I add both sides, 3.92 plus 3.92. That gives me t equals 6.19 Newton. That's how we get both acceleration and the force on the string. You can see the simulation also, and you can play with. Look at here, I use the same numbers, and our numbers are very close to that. You can play with that, or you can go step by step, or you can play with this. You can see how it works. Okay, this is a great tool to play with. You can try the same problem. You can repeat this, repeat all the steps, but with different masses. Say block 1 has mass 6 kilogram, and block 2 has the mass of 4 kilogram, and repeat all the step of example 1.